Hello, we are here for one more lesson of this T-FLEX analysis training course. And the topic for today will be something called the anisotropic materials. Anisotropic materials differ from isotropic materials because their physical properties where we can include elasticity, Poisson ratios, thermal conductivity, and others, have different values depending on the orientation of the body in space. So the isotropic materials, these characteristics, these physical properties do not change uh, depending on the orientation, and the anisotropic materials change properties according to the orientation or position in space. Among the variety of anisotropic structural materials, we have two types that we can check inside T-FLEX analysis for the moment. So we have what we call the orthotropic and the transversely isotropic, okay? And we can see briefly what we can do with one type and with the other type. I've created a very simple body, this box. We will not do any calculation with box, just to have it for the presence of the dialog box where we can define these physical properties. So first, the isotropic materials. When we have a body, in this particular case, or we could have others. So when we have a body, we have a material assigned, so in this particular case, steel. We can open the physical properties of the material, and we have these characteristics here: the elastic modules, Poisson ratios, shear modules, thermal expansion, thermal conductivity. We have the definition of units and the values here. And we can define the material structure. So we can define the isotropic. So in isotropic, you see that we have only one value. And this means that this value will be applied in all the directions of the material, independent of the orientation or the shape. But we can have also two other possibilities that we spoke. And these two possibilities are anisotropic structural materials. So starting with the orthotropic, when we open, we have the same properties, but they can be defined with different values for each of the axes. So a brief definition of this. An orthotropic material is a particular type of anisotropic for which there are three mutually orthogonal planes of elastic symmetry in respect with the material characteristics. They remain invariant. We can include in this type of materials, for example, wood, paper, veneer, and if we ignore in the example of the veneer, if we ignore the inhomogeneous spatial distribution of the fibers. We can include also composite materials, like, for example, laminated fiberglass plastics, fabric fiberglass plastics, and others. There are a couple of theoretical concepts about the Hooke's law, for example, and the coefficients of these equations. If you consult our theoretical course, we have more details about these concepts. but basically this is where we can define all of these values. There is another important topic regarding the coordinate system specified for the body, and that allow us to define the direction of the axis. So we can have these values here. And when we make a study, so we can create a study, we can say, okay, I want this guy here, this body. I'm doing something about the mesh that for the moment it's not very important. And when we have these study elements, if we open, we can do this material coordinate system. So we can define, I don't have it ready, and I think it's quite easy to understand. We can define a particular local coordinate system because having different parameters for each of the axes, it is important the possibility to define also this local system with a proper orientation. We can have a couple of other options also, as one of them is the possibility to have a path that defines an anisotropy of the element, but I will leave this as example for this particular case. We have also another type of anisotropic structure that we mentioned as being the transversely isotropic materials. And the place where we can define also this is on the same place. For the material that is defined and probably due to the shape, or if we want to define a new material, we could choose this kind of material structure, so transversely isotropic, which is different because what is presented to the user now, we can see it like this. It is grouped for the properties. It is grouped two axes from one side and another axis on the other side, but we can define, again, we have different dialog boxes. We can define also different values for these two fields. So a transversely isotropic material, it is a type of an isotropic material where each point has parallel planes of elastic symmetry, in which the material's characteristics remain invariant regardless of the orientation. The axes of this rotational symmetry are located orthogonally to the planes of symmetry. And one example of this kind of material is, for example, a multi-layer pipe in which the across layers, so along the radius, the properties of these materials are different from those along the tangent and the generating line. I think a little more easy is to identify each one of these transversely isotropic or the orthotropic by the possibility to define the physical properties different for each one of the axes, and in this particular case define it equal for these two axes. Again, we can have this definition here, and again the possibility, as I shown before, the possibility to define a coordinate system also for this particular case, because again, having different values for different axes, it was important to have the possibility also to define the orientation of the axis. I think this is a very important topic, and in this particular one, because it's not easy, I think goes a little away from the purpose of this lesson to show mathematical equations. I think it is important for the ones among you that want to see a little deeper about this topic to consult our theoretical course, because there are a couple of more in-depth explanations about the mathematical side for the equations and what is considered. I truly hope that these explanations were clear enough, and that we can, or you can start use also this new tool in your use of the software. You can check also the examples that we are releasing for different types of calculations in T-FLEX analysis. So among them there will be examples showing also these anisotropic materials or material structures. But anyway, if there is any additional help needed about the topic, you can send us a contact through the usual channels, and you can expect our support for this topic.